And this is the first time that it's happened in Asia. And we have a slogan, which is gravity is gauge theory square. That's actually where the conference began about 10 years ago. But today I would say that this is a kind of outdated slogan. It should really be gravity is gauge theory square plus all sorts of loosely related topics. But there is a general theme, which is the connection between gravity and gauge theory and how we can import ideas from gauge theory into gravity and vice versa. And you might say, why Taipei? And there I have a simple answer. It's because it's the perfect place. It's a hotbed of activity. It's one of the leading places in the world today. And the reason is because of the three stars. So there's Daniel Bauman, there's Yutin Wang, there's Xiaoshen Shen, who have really made this place hopping with amplitudes, scattering amplitudes, and gravity, and all sorts of wonderful things. So the outline of the talk is, first, I'll just say a few comments about the meeting, some of the topics that are covered, and then I'm going to give you a review of some of the basic ideas that we use. There's something called the double copy, which I'll explain, and its connection. That's the connection between gravity and gauge theory. The concepts of unitarity, which is conservation of probability in quantum mechanics, scattering amplitudes, and gravity. And then I'm going to show you two applications. Unfortunately, because this is a colloquium and limited time, I could only show you two applications. But these are really cool applications. Okay? So scattering amplitudes began with Rutherford, the idea that you can determine the basic interactions of elementary particles, alpha particle and gold nucleus, by doing a scattering experiment. Today, it's the same basic idea, the same basic setup, and virtually everything we know about subatomic particles, it's based on studies from scattering using colliders. And from the scattering angles, you can actually deduce exactly what the basic interactions are. And today, it's the same, except we use much more sophisticated tools. We use quantum field theory. In particular, this would be a Feynman diagram of quantum field theory. So because this is a fairly technical subject, I thought maybe I should have a little dictionary. Oh yeah, by the way, if you're in the conference, you're going to learn nothing here, except for a couple jokes, but they're not going to be very good. So this is really for people who are not in the conference. The scattering amplitudes, what they are, it's the basic description we use in quantum field theory for particle scattering. Here, QCD, that's quantum chromodynamics. That's the generalization of quantum electrodynamics, except it's for the strong nuclear interaction. The theory of quarks and gluons, which are the constituents of the protons, and neutrons, and so forth. You'll hear me talk about gauge theory. When I say gauge theory, I mean theories like QCD. Two examples are quantum electrodynamics and QCD. We're going to talk a lot about supersymmetry. That's the relation between the bosons, the forces, and the fermions, the matter. And this is central to many topics in theoretical physics. Virtually any problem, the first thing a theoretical physicist will do will be to supersymmetrize it, to put in this extra symmetry. And there's a couple of reasons for that. The one reason that we use is because it makes the problem much simpler. We'll hear about super Yang-Mills. That's a supersymmetric version of QCD. We'll hear about supergravity. That's supersymmetric versions of gravity. The unitarity, which is the conservation of probability. This double copy, and that's the idea that two gluons can precisely describe one graviton. Very cool idea. Okay, and the field of amplitudes has blossomed over the years. Its origins are in QCD, LAC phenomenology. Okay, then these problems are hard, so you supersymmetrize. They super Yang-Mills, which is that supersymmetric version of QCD. There's supergravity, connections to string theory, mathematics. Amplituhedron is the mathematical geometric construction that's used to understand scattering amplitudes. There's lots of mathematics. Gravitational waves, big thing where there's a lot of activity on that. And also classical gravity is part of the gravitational waves. So let me just point to a few things that were discussed. So this was supposed to be originally a conference on this double copy, but in fact, if you look under the hood, you'll find all sorts of things which have nothing to do with it or tangentially related. But like I said, the key idea is that we have gauge theory and we have gravity, and what we want to do is use the ideas of gauge theory to understand gravity and vice versa. So the first thing, of course, there were many discussions about scattering amplitudes and their structure. Non-trivial structures, endless discussions about that. People get really excited. Some structure, the double copy. Oh, here was a new one, amplitude zeros. There's certain zeros, so there's a structure there. And that really is great fun to look at. Generalized symmetries. The connection to gravitational waves is something very big that, in fact, I will discuss here. And that's to go to high precision. There's all sorts of other questions, like dealing with spin. We heard talks about QCD. Okay, there's cosmology. That was a big deal. That's thanks to Daniel Bauman. He's been trying to teach us what to do here on, it's called cosmological correlators and its connection to cosmology, early universe. Black holes, that's a big deal. There's neutron stars. I never thought neutron stars would be in this conference, but there it is. Now, the theory of scattering amplitudes, its basic place, like the place it belongs, like is collider physics, right? Because there you take particles, you smash them together, and you do a scattering process, and then you try to analyze that in terms of quantum field theory. So the natural place, say today, that you'd be thinking about scattering amplitudes is the physics of the Large Hadron Collider. For example, here's a Higgs boson event. Particles come in, particles go out. And one of the parts that's needed, a core part of trying to understand a process at the Large Hadron Collider is, in fact, the scattering amplitudes. And the conventional standard textbook way of thinking about it is in terms of these Feynman diagrams, which describe, if you were to square this, it would be a probability of some event happening. And then I'll be talking about these loop diagrams. Every time you hear the word loop, you should say higher order and perturbation theory. And these scattering amplitudes, they're a foundation for trying to understand the events at the Large Hadron Collider. In fact, that's where this field of scattering amplitudes began its life. And here would be a good example of beginning its life. So let's consider the scattering amplitude. So this would be two gluons come in, and the gluons would be inside protons, and the protons smash together. So then these gluons can bounce off each other and create more gluons. So this would be a 2 to 3 scattering process. This would be called a 3-jet event at the Large Hadron Collider. And if you evaluate this by using Feynman diagram methods, you open up the textbook on quantum field theory, you follow the Feynman rules, and then what you find is something like this. Actually, this is just a small piece of it. It's about a 20th of the entire expression. And if you take out a microscope, you can find what these little things are. They're dot products of momenta. There's polarization vectors. So gluons are vectors like a photon. So they carry polarization vectors. So that would be these things, and there would be a whole collection of terms like that. And if you look at that, you don't actually learn very much. It doesn't look like it's anything, well, that interesting. I mean, doing the calculation is interesting. Now you have a way of making an experimental prediction. But on the other hand, the structure is not that, it doesn't look so clean, or it doesn't look like you can really learn anything. And the basic problem is you're using the wrong variables. You're using those polarization vectors. What you need to use are spinors. This is called spinor helicity. These are spinor inner products. All right, here's be a spinor inner product. There's a gamma matrix. Exactly what this is isn't so important. This thing you could think of as circular polarization. It's sometimes referred to as Chinese magic. Zhu, Zhang, and Chang. This is the way they wrote it down, and this is by far the best of the best way to do it. And the key thing is that these polarizations, so these would be gluon or photon polarizations, they satisfy all the properties that a circular polarization is supposed to satisfy. And there's some reference momentum in there, but that doesn't have a physical effect, and it's a very slick formalism. Now, we'll apply it in just a second. Maybe here would be the first example of double copy. So on this side of the equation, you have two gluon polarizations. And you may notice on the other side, there's a graviton. This is a graviton polarization. So there it is. The graviton is a double copy. There's two copies. Now, you'd probably complain this is a little bit too trivial because this is the linearized theory. Non-interacting gravitons, and if I tell you a non-interacting graviton is like two gluons, you probably won't be too impressed. But in fact, this idea will be generalized to the entire theory of general relativity. All orders of perturbation theory will have this concept in it, as we'll see. Ah, yes. Let's apply a little Chinese magic there. So you see what happens. Those formulas you saw on the last page, the 2 pages ago, the messy formulas, you see, if you write it in terms of helicity variables using circular polarization, the thing completely collapses. If all the polarizations are identical helicity, 0, 1 negative, the rest positive, 0, and then if 2 are negative, 3 are positive, you get some very simple formulas. And this continues to all orders, the same amazing simplification. And then you could say this observation, this is Park and Taylor, and then cleaned up by Mungno, Park, and Q. And this observation is, you could say, the birth of the field, where people woke up and said, you know, there's something going on here. Well, at least just a few people realized that. Okay, so how do we approach gravity from the amplitudes point of view? Well, first question, how do you approach it normally? And the answer, of course, is you look at Einstein, you look at Einstein's equation, and you try to solve Einstein's equation. And all these concepts, the beautiful concepts, geometry, curvature of space and time, and so forth, and you use all that. Well, that is not the way we do it. We like Einstein, but we don't use his equation. We start somewhere else. We start with the concept that gravity is mediated by massless spin 2 particle. That's the starting point. And from there, you can actually build up all of Einstein's gravity. This is something Feynman understood. But in fact, you can go beyond that. Just rebuilding Einstein's equation is perhaps not that interesting. It's kind of cool that you could do it from this simple concept that massless spin 2 particles are all you need to build the theory of gravity. But the question is, can you do something useful with it? Is it a way of computing, a way of thinking about gravity. And this way, starting from gravitons, that is not suitable for all problems. It's only suitable around what we call flat space and perturbations around flat space. Then this is a good way of thinking about it. For problems that are highly curved, maybe you'd like to go back to Einstein's equation. Now you can ask, graviton is real. You're applying quantum gravity. You're starting to talk about quantum gravity. Is it real? Well, of course, I don't know, because the only way you could know if quantum gravity is real is not by theory, by experiment. Okay, no such experiment has been done. And so I don't know if gravitons are real, but I do know for sure one thing about gravitons. They're useful. You can use them. And you can use them to attack problems in general relativity, difficult problems in general relativity. You think of this as a complementary approach to gravity. Now, one of the ideas we're going to use, which I won't explain very well here, it has to do with what's called the unitarity method. It's related to conservation of probability. And a key concept is that we need to work with real particles, not these virtual particles. Virtual particles are a creation of humans. Real particles exist. So we like to use things that are as physical as possible. You want to consider a way that you can build up high orders of perturbation theory, that's the loops, by looking at lower orders of perturbation. That would be, let's say, a tree. So this would be a part of a lower order perturbation theory. You put these together according to certain rules as a systematic assembly. And this thing is all designed so it reproduces what Feynman diagrams would have done had you done it that way. Okay, just a different organization, and it has certain advantages for going to very high orders of perturbation theory, especially for gravitational theories. The idea, the basic idea is you build up these amplitudes. The high loops are built from lower loops, so more complicated things are built from simpler things, and they're done in a gauge invariant way and something more or less physical. And this idea, this came quite a while ago. This came from collider physics. Something called the NLO revolution was done using these ideas, and today we're going to apply those same ideas to gravity. So we're not going to use Feynman diagrams. We're going to do it by using this unitarity method. Now, what's the problem with gravity? So there's all this beauty of geometry when you start. You learn general relativity, and you're very pleased that you're learning about all these beautiful concepts. Well, as soon as you start doing perturbation theory, you discover very quickly that all the beauty gets lost. That things get very complicated very quickly. So let's suppose we had, this is called the Einstein-Lagrangian, that's the curvature of space-time. This is the metric, and the metric, let's say you do an expansion around some background. It could be flat space, it could be another curved space, and then you have the graviton field, which is the fluctuations around this space or whatever the background space is, and you just expand it out. You just series expand. You try to get the interactions between gravitons, like this would be a 3-graviton interaction, 4-graviton, 5, 6, and so forth. And you very quickly discover that it's very complicated, and that's because this is a highly nonlinear theory. So then you get quite a complication there. Now, if you look at the comparison to QCD, that's based on this Yang-Mills Lagrangian, and that has 3-point interaction, so 3 gluons can interact, 4 gluons can interact at a point, and then it stops. And you look at these two and you say, I guess gravity is a lot more complicated. Well, let's see, is that actually true? In fact, well, let's look a little more carefully at what these interactions look like. So if you just proceed straightforwardly and you see how do these three gluons interact, you can find this in your favorite textbook on quantum field theory, three gluon interactions. You get something, it's a little bit complicated, but not so bad. If you look at the interaction of gravitons, that's quite a bit messier. And in fact, this notation here is hiding a lot of the mess. There's a sim here. It says you're supposed to symmetrize between the indices because a graviton is a symmetric tensor. There's a P6 here. That P6 says it's 6 terms. So there's 6 terms here, permutations. The P6 means that there are 6 independent permutations of that term. And you get some big thing, and you say, gee, that's pretty messy. That definitely doesn't look good. In fact, suppose you go to the on-shell way, and you're supposed to use the physical relationship between energy and momentum. That's Einstein's relation. And if you apply Einstein's relation, let's see what happens. So you declare that these gravitons here are real, like physical gravitons. These gluons are real, physical gluons. And you apply this. Well, the Yang-Mills theory doesn't do very much. They could clean it up a little bit, but not very much. But if you look at the Einstein gravity, you see it completely collapses. And in fact, you can see that it's 2 copies, right? It looks like 2 copies. See this? There it appears once, twice. It's the square of the Yang-Mills theory, right? That's the first, you can say, non-trivial example of a double copy. It's just a little piece, though. It's only this 3-point interaction. And you might ask, well, but what about more complicated things? What about the entire theory? Well, there is, back in 1985, there's Kawai, Llewellyn, and Tai. Professor Kawai is right there. It's very good. Yeah, raise your hand. They're looking at you. Anyway, this is a really beautiful relation. This was derived in the context of string theory, but we know field theory is a low energy limit of string theory. So if you derive something in string theory, and then you take the low energy limit, you have derived something in field theory. These are remarkable relations. What they say is that the 4 graviton amplitudes, this is an amplitude, there's 4 gravitons on this side. This is gravity here. And on this side is gauge theory. And it says that if you want the 4 graviton amplitude, don't calculate it. Just do these simpler amplitudes of gauge theory, and then multiply, and then put, this is a kinematic invariant, you put a factor here, and you're done. And it's a set of formulas that you can use for any of these tree level. So it's like 5-point, the lowest order of perturbation theory, 6-point, 7-point, all at the lowest order of perturbation theory. And this is, you'd say, the first clear example of gravity is 2 copies of gauge theory. And this works for any number of legs at tree level. So what's really remarkable about this is it's a statement that gravity is derivable from gauge theory. They belong together. It's not like there's this theory of gravity out there and there's this theory of QCD out there, and they're just completely different. Right? One is geometric and one is based on quantum field theory, and they're just different. Now this says, they're basically the same thing. And it tells us a specific mapping between the two. And probably the most important part, it's not just some specific sets of theories where this holds. It's very generally applicable. And in fact, we're going to use it in the physical world to study, for example, black holes. We're going to use exactly this idea. Now, there's a reformulation of these KLT relations, which is very cool. That's this duality between color and kinematics. By the end of the talk, I'll have this thing worked out. The duality between color and kinematics. So let's look at this 3-gluon vertex here. So there's a coupling constant, very much like in electrodynamics. There'd be electric charge, and there's a coupling constant there. There's something called a color factor. That's just a matrix that tells us how the different gluons interact with each other. This is just a matrix of numbers, and then there's this vertex here, the momentum-dependent kinematic factor. Now, this theory is based on a Lie algebra. There's a set of generators, and they satisfy an algebra. And this algebra, every time you have an algebra, there is an identity called the Jacobi identity, a consistency relation. The Jacobi identity says that these are called structure constants. They have to satisfy a very specific relationship. It's basically in terms of Feynman diagrams. It's the color factor of this guy plus the color factor of that guy plus the color factor of that guy. You add them up, you get 0. So that's a constraint. Okay, and that's well known. You'll find that in every textbook on QCD, on non-abelian gauge theory, or Yang-Mills theory. Now, let's start with Feynman diagrams. With Feynman diagrams, there can be this contact interaction. Let's get rid of that by using this fantastic identity. One is S over S. So S would be one of these. There's a pole here. So there's a kinematic pole like 1 over S here. 1 over S. So I'm going to multiply and divide by 1 over S. I look in here, I find a color factor that looks like that one, and I use this great identity to put back the missing propagator. So I'll write the amplitude in this form, 3 propagators. There's a kinematic numerator, and that comes from algebra having to do with this kinematic part, and then a color factor having to do with a little algebra that comes from this color factor. And you can go home and check this. Take out any textbook on quantum field theory, Feynman rules, and work it out. Once you put it in this form, this 4-point tree amplitude, but these legs have to be physical. They have to satisfy Einstein's relation. So that the energy square is equal to momentum square for massless gluons have to be satisfied. Then you'll discover something a little bit surprising. You'll find that these numerators, they satisfy a constraint, that they satisfy the same identity that the color factors do. Now, you say, that's kind of weird, but okay, what do I do with that? It's just a little curiosity, right? It doesn't look like much. But in fact, this has everything to do about gravity. The secret of perturbative gravity is right there. Okay? And the way this thing works is, let's take a tree amplitude, and we're going to put it into a form. And this requires a non-trivial rearrangement. 4 points, it was easy. At higher points, you have to rearrange it. And we will arrange it so that you get the correct amplitude. But for every color identity, there's a similar identity imposed on the numerators. And you can verify that you can still get the correct amplitude like that. So here's the prescription. Suppose I start with gauge theory, QCD. I want gravity. I take the color factor and I replace it with the numerator factor after making them obey the same algebra. There it is. I get Einstein gravity, just like that. Now, that looks like magic. In fact, it is. This is magic. And the definition of magic is that we don't actually understand what the underlying algebra is. So we don't actually understand where this comes from. But what the heck? You can still use it, right? As long as you know it's true. And just to be clear, these numerators are these kinematic factors of momenta and polarizations. And you see the two belong together. Right? The dynamics of the theory is determined by this numerator. And the same numerator, here it's squared, there's just one copy, there's double copy, right? It's the same, right? Gravity and gauge theory belong together, like really belong together. And this definitely is crying out for some kind of unified description of gravity with gauge theory. They belong together. Perhaps it's along the line of string theory. Now, here's a conjecture, which is going to come in a little bit later, that you could do this to all orders of perturbation theory. If I had, let's say, this would be a 3-loop example. I pick 3 diagrams, and the color factors obey this Jacobi identity. So the conjecture is that there's always a way that you can readjust these kinematic numerators, the kinematic part, so that the same identities are obeyed. So let's say you find something like that. You force this to happen. But you still, it has to be this correct amplitude. So you start with the correct amplitude, you move terms around in just the right way so that the kinematic numerator of gauge theory satisfies the same Jacobi identity. Suppose you've done that, then it's actually straightforward to prove that you're going to get gravity simply by taking the color factors and replacing them with the kinematic numerator. That's very cool. The hard part in this is right here. Can you find such a representation where this is satisfied, where these numerators have the same algebra as the color factors? And to this day, this remains a conjecture. This has not been proven. One problem, which I will come to later, is as you get to very high orders of perturbation theory, it can be very hard to find these representations. And that's actually a big trouble because it stops us from doing gravity. In fact, there's no other way to get to the very high orders. I'll be talking about 5 loops, but it's very high orders of perturbation theory. There's no other known method to get to those high orders except through this, and if you're being blocked, that's not good. Okay, so let's talk about applications. So what I just showed you is that in a precise sense, gravity definitely is meeting QCD. It meets it this way. If you want gravity, there's a prescription that tells us copies of gauge theory allows us to build gravity theories. The applications we're going to talk about, one is multi-loop supergravity. It's to study what's called non-renormalizability. It's whether the theory has controlled divergences or not. And the other one is very cool. It's the application of these ideas to try to do high orders of perturbation theory for the gravitational wave problem. Let's say 2 black holes, it could be neutron stars, and you want to try to make precision predictions for the gravitational waves. So let's start with the first one, the short distance behavior of gravity. So I'm sure you've heard these things. Einstein's theory of general relativity is incompatible with quantum mechanics. I don't know, maybe you read Brian Greene's book or something like that. That statement is kind of silly on multiple levels. It's a pretty screwed up statement. But normally, what they really mean is this one. This is at least more precise. All point-like theories of gravity are divergent and non-renormalizing. So let's answer some questions. Where do these statements come from, and are they true? Well, the place it comes from is actually something very simple. It has to do with the fact that gravity is controlled by Newton's constant, which is dimensionful. And as opposed to gauge theory, which is controlled by, say, a constant called g, little g, and that carries no dimensions. And then there's some simple dimensional analysis. Well, let's see, if this thing carries dimensions, then to get the dimensions right, I need more powers of momentum on in the perturbation theory. See, every time I put in a kappa, I got to put in another p. And if I have an integral, that's a loop integral, so that's high orders of perturbation theory. This one would be 1, 2, 3, 4, 5. So it would be 5, L equals 5, and I have some very complicated integral. But you can see that if you take p goes to infinity, and I put more powers of p in the numerator, then what happens is this integral for gravity will have a poor behavior, certainly poor compared to gauge theory. And that's the origin of the non-renormalizability problem, that you will encounter worse and worse infinities in the perturbation theory as you go up in orders of perturbation theory. Okay. Now, this is the basic crux of the matter. You can get very sophisticated, especially in supersymmetric theories, right? Lots of very complicated papers using supersymmetry, but at the end, it's the basic idea. There's some kind of counting. You do some power counting. And then from the power counting, you get some bounds, and then from the bounds, you then make a pronouncement about whether there's infinities. The more supersymmetry you have, the better the short distance behavior. That's a well-known property of supersymmetry, that bosons and fermions cancel each other. Their contributions cancel each other in this limit. There's some cancellation. But by following these arguments, they're basically done one diagram at a time. And the basic problem with any argument like this, based on a power counting, where you're counting up the p's and you're counting up the integrals, is you have to worry about hidden cancellations. And I don't mean hidden cancellations that the theory doesn't know about them. The theory knows about them, but us humans, we don't understand how to extract those cancellations, that they don't work in a normal way that we're used to in H theory. Now, there is a theory which I'll talk about, maximal. It's called n equals 8. That's the maximum number of supersymmetries. I should say supergravity. So that should have the best behavior. Uh-oh. Oh, that's not good. Okay, there, it woke up again. Okay, that was not my fault, but, oh, I'm going to, oh. Okay. So, the question we want to look at is in supergravity theories. These are well-defined theories, right? There's a set of rules, and if you're arbitrarily strong, you could go calculate and answer questions about the theory. But there's a very simple question. These theories, these supergravity theories, are they finite or are they infinite? Right? If you calculate with them. And these theories have been around for 50 years. You might think after 50 years, a very simple question like that, you'd know the answer. Now, if you stop someone on the street, the average physicist, and you ask, what is it? Certainly the most plausible answer is it's divergent, and this is accepted. Now, are these statements correct? Well, here's actually a kind of cute quote. This is Hawking. So back in 1984, he wrote something which I'm very amused by. He said, "It is not clear that general relativity, when combined with various other fields in supergravity theory, cannot give a sensible quantum theory. Reports of the death of supergravity are an exaggeration. One year, everyone believed that supergravity was finite. The next year, the fashion changed, and everyone said that supergravity was bound to have divergences, even though none had actually been found." Now, 30 years later, we obviously know quite a lot more about it, but unfortunately, we still don't have the answer for Hawking. Right? Does it diverge? Does it not diverge? So actually, let's look at a scorecard. So, of course, people make predictions. They have power counting methods. Over the years, all sorts of groups have made predictions that there will be divergences at 3 loops. This would be in the 80s. 5 loops. There's us. In 1998, we were pretty confident that there'd be a divergence at 5 loops. So I'm going to make fun of people, so notice we're included. You know, and then so on, and there's all the way down to 9 loops. Well, let's see how people have done. And the way we actually know this is because we calculate. We have the methods. We use the double copy. We use unitarity. We use those tools that I told you about. And basically, instead of arguing about it, and believe me, people would argue a lot, you just calculate the damn thing. It's hard to calculate, but if you have the tools, you can just do it. And you can see pretty much everybody is wrong. Okay, we never reached 9 loops, but this result, this one was retracted. There is one. It's this half-maximal supergravity. This one actually does have a divergence, but it turns out that there's something very special about it. It has something to do related to anomalies, which are violations of symmetries. So unfortunately, after all this calculation, you see, things are still a little bit murky. Okay, so let's have a look at what what the community says, and this is based on sharpening the symmetry arguments, because as you learn the truth and you dig harder, you can really push and learn what the symmetries of the theory tell you. Okay? And there are all sorts of predictions in half-maximal supergravity. Let's say, oh, hey, that's not what it should have done. I hit the laser button and the thing. Oh, there we go. Let's see, there's half-maximal supergravity. Okay, d equals 5. So this is 5 dimensions. So it's just a case that's interesting and easy to calculate. And n equals 8 supergravity. This one's in a weird dimension. Don't ask me what d equals 24/5 is. What dimension is that? But never mind, you do it by some kind of analytic continuation. And this is the prediction. Okay, so of course you could resist with predictions like that. You want to do some calculation. So let's look at these cases. And once again, you find pretty much everybody is wrong except 2 cases. It's not behaving correctly. These predictions, they're missing. Whenever it's missing, this is a highly non-trivial cancellation. All the symmetries have definitely been used up of the normal kind, or the normal interpretation. If you see that something is wrong, it means that there is some extra cancellation which is not understood. And it's definitely not of the normal kind of cancellation that you would find in a gauge theory. Here's one that does exist. This has something to do with an anomaly. This one's a little weird. It's that unphysical dimension. It looks like the unphysical dimension was a problem. There's actually some people in the audience here showed that if you look at pieces of the amplitudes called unitarity cuts, then in fact there are extra cancellations, which deepens the mystery. It means we should go calculate. Okay? And one of the key points is this origin of these cancellations. They are still not understood today. Now, let me just show you an example of one of these cancellations. So this is a great example. It's n equals 5 supergravity, so it's less than maximal. It's a 4-loop calculation. That's a serious calculation. You need some Russian help. In fact, this thing is so complicated, 2 Russians were needed, not just one. Okay, there's n equals 5 supergravity is built out of n equals 4 super Yang mills and n equals 1 super Yang mills. And if you look at these pieces, you see immediately that they're divergent. But when you add it all up, let me show you what happens when you add it all up. Those are the pieces. They're divided in some way. And when you add it all up, you get 0. Now you're probably saying, that's pretty stupid. Why did you do that long calculation? You should have just figured out the symmetry. The symmetry, why this thing is 0. That's exactly the problem. Nobody knows the symmetry. So nobody knows exactly where to start. And people have invested quite an effort into finding the symmetries, and okay, nobody knows. Okay, so now you could say, okay, why haven't you made more progress? That's actually from a few years ago there. And the answer is there's a problem, and it's the problem that I mentioned before. It's very difficult to find these representations of the amplitudes that are that satisfy this duality between the color and the kinematics. And if you don't have that, you're basically screwed, because then you cannot do the gravity. And a good example of that is n equals 4 super Yang-Mills we've never found such a representation. We were actually able to do the supergravity, but that involved lots and lots of tricks. That was not completely straightforward. Okay, and there are a couple calculations that need to be done, which we can now do. Now, I'm not going to explain how to do it, but I will say, come to my Friday talk if you're interested, and there I'll explain what the trick is, the resolution to this problem. So now we can go on, and there's now lots of things to be done. You know, some obvious things that need to be done are, we want to look at the next order of the n equals 5 supergravity. 4 loops had an enhanced cancellation. So you might as well have a look at 5 loops, try to understand what's going on there. There's progress in n equals 4 super Yang-Mills. The amplitude is known, but it was unknown how to turn it into supergravity. Now we know how to do that. And I think in the coming years you're going to see a lot more about this now. Okay, so the second one, I see I'm running out of time, it's gravitational waves. So the era of gravitational wave astronomy has begun. And I can tell you, when I started working on it, I heard that the first event was brighter in gravitational wave radiation than all the stars in the visible universe are in electromagnetic radiation. That's very cool. So that had to be something I needed to work on. And there are quite a few talks. Here would be 3 talks, review talk, and technology talk. Now you may ask, what does particle physics have to do with gravitational waves? They're completely different problems. Okay, so for the problem of collider physics, we use quantum field theory, we use gauge theory, we use QCD. The trajectories are unbounded. For general relativity, we use classical physics. Yeah, but the answer why you can use quantum field theory for this problem is actually very basic. It's concepts from effective field theory. If you have a separation of scales, so you have long wavelength radiation, you have the 2 black holes are far apart compared to their size, then these things are points. If these things are points, then that's in our wheelhouse, right? Point particle theory. Never mind they're gigantic, kilometers, but relative to the other scales, they're points. And then we go ahead and we use quantum field theory. This was systematized by Goldberger and Rothstein. They explained the basics of the EFT setup. And the idea is we want to improve the predictions for the in-spiral, and there's also the merger and the ring down, but we're going to focus on the in-spiral part. And the in-spiral part is where we can use perturbation theory, because the 2 black holes are still far enough apart that the perturbation theory is valid. As it turned out, there's a paper which gave us instructions. This is from Thibaut Damour. And actually, it's kind of fun to read this, what it says. I've never seen a paper like this. Because there it is in the abstract. You don't even need to read the paper. Right in the abstract, he says, And we urge amplitude experts to use their novel techniques to compute two-loop scattering amplitudes of scalar masses from which one could deduce the third post-Minkowskian effective one-body Hamiltonian. I've never seen an invitation like that with that kind of clarity, so there it was. Now, why do you want to go to high orders of perturbation theory? And the reason is because the detectors are going to undergo a vast improvement. If you look, there's where we are today, and then you look at the future, Cosmic Explorer, and you say, oh, that's a factor of 100 in sensitivity. This is a sensitivity. This is 100 times more sensitive. How many orders of perturbation theory do you have to go to get another factor of 100? Probably 2. Now, these orders of perturbation theory are pretty serious. You know, you want to get, it works out to be, you want to get to 5 loops at least. You want to get really high. Okay, and the solution of the problem of gravitational waves, it doesn't come from one method. There's all sorts of different methods. So if you look at different regions of the parameter space in this cube, there's mass ratio, there's separation between the two black holes, eccentricity. If you are at small separation, small mass ratio, numerical relativity. Post-Newtonian would be large separation and small eccentricity. Post-Minkowskian, that's the one natural for us. That's what fits with amplitudes. That would be valid where you have large eccentricity and large separation and any mass ratio. And there's gravitational self-forcing. You've got to put all of this together into some kind of a model that does an appropriate interpolation and resummation and so forth. For that, you should go to Alessandra Bonanno's talks. I think Monday Colloquium. Go to her talk. She'll explain all of this in some detail. And this is actually from 2018. She's kind enough to come to amplitudes and tell us what they wanted. So what this shows are orders of Pn, post-Newtonian. You go to these columns, so it's different colors mean what's been done. And then she pointed out, look, if you could do this third post-Minkowskian order, so that would be to third order in G. Well, first you get a piece of this post-Newtonian that's never been done, and then this would be something to go ahead and do. So the instructions, like I say, were very clear of what was important to be done. And the way it's done, the basic idea is you take two communities, you put them together. Amplitudes community, it's put together with the effective field theory community, and then you can go ahead and compute post-Minkowskian observables. And there have been many talks related to this at the conference. And one of the things that's really remarkable is when we started this is that these ideas that I was talking about, the unitarity, it fits very well with the problem we're facing. And that has to do with the idea that we're interested in long-range forces, so they're well separated, long-range forces. And the long-range forces requires be a propagator there. And the requirement of there being a proper propagator there, we can reinterpret in terms of these on-shell conditions. And so it turns out that the method and the problems that we're interested in, they work very well together. And this, you see the double copy, we apply it, these are tree amplitudes, 3 point, 3.4 point. Double copy works very well there, and then we sew this together to make loops. That's something very natural. Make a long story short, here's an answer. This was the first answer we got. This was third post-Minkowskian order. It's a Hamiltonian, a two-body Hamiltonian. It tells you the interactions between here and here. If you look carefully and interpret all this, you'll find Newton is sitting in there. It looks very complicated because it's all orders in velocity. It's Lorentz invariant. So it includes all the special relativities included in here. The next order of post-Newtonian, Einstein, Infold, Hoffman. You'll find it hiding in these two pieces. But the key thing of all of this proves is, not only does the calculation, but it proves something philosophical. You can actually do calculations of interest to the general relativity community. Now, when we did this, you might imagine we start talking about, this double copy, unitarity, this, I don't know, very strange stuff. So you can imagine the first question that the general relativist had: how do you know it's correct? Well, of course, we were very worried about that, so we did lots of checks by doing certain expansions, and then you compare to the literature. And of course, we passed the checks, otherwise we would have published. And needless to say, there was a little bit of resistance to the answer. There were various questions. That resistance had something to do with a puzzle at high energies. But in fact, all we had to do was wait until various people would do calculations in a more traditional way, and they would compare in the overlap, and indeed, everything was fine. So, especially given the initial skepticism, which was very good because the formulas were tested. And I'm happy to say that now the community accepts that, in fact, this is correct, and the methods actually do work. And they also work to much higher orders. Maybe just a quick thing. This has been pushed to next order, g to the fourth. We're working on the next order, g to the fifth. There's a problem having to do with integrals. It's all about being able to do integrals. And I should add that technology is all imported to collider physics, from the amplitudes and collider physics community, how we do the integrals of general relativity. They're the same style of integral. Oh, here's a nice plot. I'm almost done. So the question is, okay, does it help? So these are the general relativists, of course, very interested in this. There's Donano's group, Damour's group. This plot is from Damour and Tango. No. And it shows what happens, increases of, if you go up in orders. Something has been done here to make it valid in the region where it shouldn't be valid, right? This is perturbation theory. And what happens in this region, it's strongly coupled. Perturbation theory shouldn't work. But you do a resummation. It's called effective one-body approach. It does a certain resummation. And you can compare it to numerical relativity done in an overlap region. And you find an amazing agreement. Absolutely amazing. And this is not good enough for the future. The main thing you learn from this plot is we should go on because it works, right? We're making progress. And Alessandra is going to explain that in her colloquium and also in her talk at the conference. Outlook, well, okay, I'm not going to discuss, say anything in detail, except lots of people are working on all aspects of the gravitational wave problem. So pushing higher orders, which is what I discussed, is waveforms, finite size effects, tidal effects, essentially, spin, absorption. There's a pretty good-sized army of people. Maybe some people are here working on this. And this formalism is far from exhaustive. I think people are having so much fun that there's no stopping it. Okay, so the summary is scattering amplitudes, they give us a new way to think about problems in classical and quantum gravity. There's generalized unitarity, double copy. They offer a unified framework for perturbative gravity and gauge theory. We think of them together in the same way. We share the tools and concepts. Direct high order calculations become possible in quantum gravity, specifically supergravity, all the way to 5 loops. There's still some puzzles that still have to be resolved, but I mean we have some new ideas that sure will lead to some new progress. And by combining these effective field theory ideas with these amplitude ideas, we get a useful tool for gravitational wave physics, and there's certainly been really amazing and rapid progress. And this viewpoint that amplitudes and gravity, from amplitudes, that gravity and gauge theory belong together, it's something very powerful, and having QCD meet gravity, it's something very fruitful, and I think in the coming years we're going to have, of course, more conferences, amplitudes, QCD meets gravity, and I'm looking forward to all the advances. Okay, thank you.